beginning of today, Professor Majumdar also mentioned, or some other, that we had to do, apart from statistics, mathematics, economics, we had to all take courses in geology, which of course Chamala Madaka mentioned, then botany, zoology, and chemistry, physics. And then many students at that time used to ask, what is the big deal of learning so many things? And somehow I got interested in, I always had diverse interests, so got interested. And then after PhD, naturally I was in a path of getting accomplishment in pure academics. So I stayed in my area for 10 years. After I got my full professorship, then I thought, let me explore what I learned before. So one of the big advantages of taking courses in other subjects, that at one point I was really motivated by Mahalanobis and JBS Halden, and at that time I decided, okay, let me try to apply statistics in other fields. So I was very much into that motivation, and I'm happy to tell that almost whatever subjects I studied at BStat, I applied in every area. So I have fortunately publication in all the areas I learned, including botany, where some plant genetics there. But anyway, but today is another thing I have to be very happy to tell, that what is my connection with CR Rao. I was not his student, and when I joined at that time, Mahalanobis was the director, and 1971 he passed away, and then CR Rao took over. So we had a huge distance between him and me. But then after CR Rao retired from India, and then he went to US first for a visiting faculty in Ohio State, then with Pittsburgh, and then Penn State for many years. I mean, still retired from there. We became much closer. So I'm very happy to tell that we wrote 2 books together. In a way, they are both editorial volume. One was the Handbook of Statistics, which was mentioned, series 25. And the other achievement which I felt is that CR Rao was never a Bayesian. And my training was very much into formal decision theory and Bayesian methods, because my advisor is very much, and his advisor. So my legacy is like Jim Berger, and then Larry Brown, and then Jack Kiefer, then Wolfowitz. So that kind of tradition I try to maintain. But so CR Rao, the volume number 25, if you look at it, it's the Handbook of Statistics on Bayesian Statistics. So nobody thought that CR Rao will write something together with me in Bayesian statistics. So that was, but you probably may not know that how much he was knowledgeable about the Bayesian statistics. He never wrote any paper or published, but he knew everything. He was just so brilliant. And after that, of course, out of the book, we actually have another publication where a selection of certain papers on Bayesian statistics. So then I went to Penn State a few times, and then we got much more closer, and then talked about different things. I mean, whatever ideas I had, I told him, even if he never worked, but he could always comment on that. That was just amazing at the age of even 75 onwards. Also, there are quite a few conferences in his honor. So I attended one in New Shuttle, and Partho was there, but he did attend the meeting anyway. Then there was a big 80th birthday celebration in San Antonio, Texas, where we all had a nice mug with Kramar Rao inequality written there. So then when I was really excited when Partho actually invited me to give a presentation on inference, because whole life I'm doing inference. And inference is nothing but, in many students here, I think students may forget, rather maybe scared of it, but it's really making a decision making. So these days, the formal inference, early days, and now it's become more decision theory, and then decision theory decision making process, and ultimately it has tremendous application in data science. So my goal will be not only talk about the foundation of statistical inference by CR Rao, but where we are leading to. So I will spend less time on past, because many other distinguished speakers already mentioned. I'll talk more about where is the future. And I'm convinced that after doing some other study, after his invitation, that his legacy will continue for many, many years, because now it will be taken by not just traditional statisticians, rather data scientists, electrical engineers, computer scientists, very much. I'll give some examples. So there are many major breakthroughs of Dr. Rao, even in inference, because he has worked in so many different areas. So when he asked me about inference, then I was first thinking, well, everything, because my first book, I got it as a gift, was Linear Statistical Inference. In first year end, there were some prizes for the students, and we had a bookstore called Saraswati Pustakala. I used to go there and then bought my first book on CR Rao's book, Linear. And after that, the book is a paperback. Now it's a hard copy. So in my library, I have 4 copies of that book. That book is still you can teach quite a bit. Then I have a book on linear models. So many of these problems are extracted, source extracted from that book. Okay, so again, I have some selection bias. So even in inference, he did a lot of work. I just picked up 3 things. And you can see that why these 3 things, because in my mind, I am convinced that these 3 things are the most important contribution of Dr. Rao in inference, apart from many other fields. So Cramer-Rao bound, or Cramer-Rao lower bound, Rao-Blackwell theorem, and score test. So what I'm going to tell about, like, first this non-technical part, I will go over this quickly, which all the students should know. At least the first 2, every BSc, MSc student must know. Third one, maybe some, may not be some. I checked with some of your professors. I know what you are supposed to know. Okay, so with that in mind, I will tell you a few things which are nothing new. And the second part of my talk, I will give a very nice extension of Cramer-Rao bounds. So in statistical estimation theory, inference, you know, is divided into 2 parts. One is estimation, other is hypothesis testing. So where both areas, CR Rao has tremendous contribution. The Cramer-Rao lower bound, or CRLB, or Cramer-Rao inequality, 1945, already heard the story. It has other names also, because it has a lot of application outside statistics, like information theory, because it actually gives a very good idea about the information matrix, Fisher information, and how it connected with propagation of information. So then Fréchet, Darmoy, Cramer-Rao inequality, different names, because different literature, as you know, sometimes use different terminology, different names pops up. It expresses a lower bound on the variance of unbiased estimator of a deterministic fixed through unknown parameter. The bound states that the variance of any unbiased estimator is at least as high as the inverse of the Fisher information. Okay? Everybody comes with the formula first, but what you see in the formula, the boundary states that it is at least high as the inverse of the Fisher information. An unbiased estimator which achieves this lower bound is said to be fully efficient. So that way, actually, efficiency of estimation also came from CR Rao's idea. Now, there are lots of applications. And many of the applications I expected, of course, Professor KRP Arthashrathu will, since he couldn't come, he will talk. But otherwise, I would take more about the quantum parameter estimation. But all I'm trying to tell you, the applications outside mathematical statistics, which many of you may not be familiar, especially the students. And these are very new work, and then there are massive direction going on in these. Like one is the first part everybody knows, is the inference in maximum likelihood estimation. That is the initial motivation. So where the Cramer-Rao bound is going now, So those will be highlighted. One is the quantum parameter estimation. Because of that talk, I didn't prepare much, but so I won't go into its more complex stuff. Quantum metrology is really the measurement of quantities. And here, this lower bound plays a major role because we cannot do anything better than that. So it gives a boundary. And then the generalized Cramer-Rao bounds, which I will talk about. But new Cramer-Rao bounds for quantum metrology, there are some references. If anybody is interested, you can share this thing or take a picture of it. And okay, so I will talk more about Cramer-Rao lower bound, where it is going now. So Rao-Blackwell theorem, that's the next, I shouldn't say rank any of them in that order, so all three. So Rao-Blackwell theorem or Rao-Blackwell-Kolmogorov theorem, because Kolmogorov came in the picture later on, is a result which characterizes the transformation of an arbitrary crude estimator into an estimator that is optimal by the mean square error criteria or any of a variety of similar criteria. Okay, so what it tells you that many problems we have to do some estimation. So a statistician's job is we look at the data and first we try to see whether we can develop some model. That model can be a process model, that means it may be coming from an economic process or a physical process or biological process or behavioral process, which is much harder. So with that guideline, and then we have the data modeling. So there are two aspects of modeling which comes in these days challenging big data analytics. One is the process modeling, other is the data modeling. So when we have a data, we always try to identify certain parameter of the model, say mean of some process. In that case, we have collected data, so we calculate the sample mean, for example, or many other estimator. Sample mean is one estimator. You can have sample median, mode, and so you start with any arbitrary crude estimator, because initially we don't know. But this approach is the unique approach which actually tells you further that the Rao-Blackwell theorem states that if g of x is an arbitrary estimator of a parameter theta, then the conditional expectation of gx given tx, where t is a sufficient statistic, is typically as good as or better estimator of theta. So you start with like what is the exact distance from here to Delhi. So you may go by roadway, by train, by flight. Flight will be accurate, of course, but if you go by drive, you want to verify. You can have multiple estimates the way you go. But then if you can find out the sufficient statistic in this problem under a certain statistical model, then this conditional expectation will give an estimator which you cannot beat. So sometimes one can very easily construct a very crude estimator gx and then evaluate that conditional expected value to get an estimator that is in various senses optimal. So that's a big achievement. You can think in practical application. Yes?
I'm surprised that there's no condition on G. That is very surprising. Not, am I right?
No, gx, expectation of gx given tx.
So the surprising thing is
Yeah.
on G.
Right. There's no question.
An arbitrary function.
Yes. Oh, you are adding that. Oh, yeah, sure. That means it's a very robust. Yes, definitely. Yeah, feel free to not only ask questions but comments if you want. Okay, the Rao-Blackwell theorem is one of the most important theorems in mathematical statistics. But I don't want to bias anybody in the literature of mathematical statistics, because sufficiency is a very important concept. Like now in modern day big data, it's called data compression. So in that case, we can throw many of the data and save that compressed value like a mean or median or something. Improved with respect to variance by an unbiased estimate, which is the function of a sufficient stat. Hence, the class of unbiased estimators which are functions of a sufficient statistic constitutes an essentially complete class. However, such a raw Blackwellization of an unbiased estimator does not necessarily provide a UMPUE. So there are a lot of other issues there, where the first question is whether we should restrict to the class of unbiased estimator, because as a decision theory, unbiased estimator behaves very nicely, but a lot of cases it may not make much sense. So a decision theorist always try to make a best possible or optimal decision, quote, under certain condition. So in that case, sometimes we may go beyond that, and therefore we put everything in the form of a decision rule. That means we have a loss function in our mind. So when you're dealing with the unbiased estimator, the loss function typically is the variance, which is a special case of mean square error. And everybody knows what is the mean square error or root mean square error, whether your engineers prefer root mean square much more. So Lehman and Sheff in 1950 showed that if there exists a complete sufficient statistic, then the raw Blackwellization with respect to the statistic produces UMVU estimator. Now all these things which you are actually study in your coursework. But what is the application? In fact, you will be surprised that some of the applications are very, very new applications. Standard application many people already do. So one is you probably know, some of you heard, like Markov chain Monte Carlo method or Gibbs sampling, which actually plays major role in Bayesian computation. Now, there, raw Blackwellization of samplings, that means you, instead of exact inference, because that involves integral, we a lot of time take samples from that. And sample-based methods are extremely popular, or simulation, outside statistics, because when you are solving a big problem, a lot of time analytically expressions are intractable. So we have to take sampling-based method. So interestingly, my friend, classmate George Casella and Christian Robert, biometric in '96, they had a paper, raw Blackwellization of sampling scheme. That means you get a lot of samples from the posterior distribution, and then you raw Blackwellize, and then you get a much better Bayes estimator or Bayesian decision making. Raw Blackwellized is extremely used in particle filtering for fault diagnosis. Now, particle filtering is one of the area, or called sequential Monte Carlo method, is extremely popular in, and why popular? Because there is no other way in signal processing literature, electrical engineering problem, and many high dimensional Bayesian computational techniques. So there, raw Blackwellization of particle filtering is there. Now each of these takes a lot of time to explain, so I am highlighting these problems. Raw Blackwellized particle filtering for dynamic Bayesian networks. You know, all of you students, I think, not, I shouldn't say all, many of you using Facebook, which is a social network. So network, statistics in the network is a huge area. And that area is extremely popular, and it will be continue for many years. And not only is a social network, but many biomedical system, biome projects, gut biome, they are all connected through network systems. And in particular, when we use Bayesian network, raw Blackwellized particle filtering is used a lot, because otherwise computational techniques are intractable. So there are some reference on that. Then other problems which are becoming very, very important in big data problems, people tracking with anonymous and ID sensors using raw Blackwellized particle filter. This is a very interesting, beautiful application of people tracking. That means these days people are using mobile phones, and then they are going different places. And then it is, through these, you can actually track the person. And the tracking, of course, may violate some rights, but it's becoming a very important tool in many government and many other agencies. So there it's used. Then for particle filter for eigen tracking, like tracking in electrical engineering is a big issues like you track also or location of airlines moving or tanks moving during the warfare. So in that case, how you have data at multiple points and you can generate the whole path through these techniques. And then target detection and target tracking. So there are some, you can see that some of these publications are not only very new, but also it has moved away from statistics like electrical engineering, information engineering, data fusion, and all kinds of new artificial intelligence. So many of these are surveillance systems people are using, and it will continue using. That's why Rao legacy will continue, I think, at least, I don't know, of course, forever it may be. Okay, the third one, as I mentioned, is the score test. The score test assesses constraints on statistical parameter based on the gradient of the likelihood function, known as the score function. Now, all of these Cramer-Rao inequality, I didn't write the formula. Next presentation, I'll write the formula. You will see that Cramer-Rao lower bound, we have the 1 over Fisher information, or if it is a multidimensional inverse of the Fisher information matrix. So you can immediately see that everything is what is Fisher information? It's really a second derivative of the likelihood function. So Dr. Raos, one of the things which, without asking him, I can guess, like how he developed different areas just from the likelihood function. So likelihood-based inference, likelihood-based estimation, and now moving to likelihood-based testing problem. So we need del F or del 2F. So in this case, and that's what all the regularity conditions you need, known as the score function, evaluated at the hypothesis parameter value under the null hypothesis. Intuitively, how he came up, if the restricted estimate is near the maximum of the likelihood function, the score should not differ from 0 because it's the derivative. It attains like here, and then the derivative where is the maximum should be flat, so it is 0, by more than sampling error. While the finite sample distributions of score tests are generally unknown, it has an asymptotic chi-square distribution under the null hypothesis. So first proved by Rao in 1948, this can be used to determine statistical significance. So Rao's score test is an alternative. It was mentioned earlier. Likelihood ratio and wall test. These tests, 3 tests, are fundamentals in statistical literature on testing of hypotheses. All these tests are equivalent to the first order of asymptotics, but differ all this to some extent the second order properties. No one is uniformly superior to the others, but many problems it can be shown that Rao's test has more second order efficiency. Now let's talk about various applications. Econometrics, it was mentioned earlier, so I'll give some references, but very important issues like one of the area now, because we have geocoded data, geospatial structure, because of GIS is there in everywhere, like your your Uber driver he is using, and Ola, and all of them. So therefore, spatial statistics is taking a big edge now for future applications, and current and future. So here, Rao's score test played major role. In fact, I'll mention some references. Then reliability, it is used. Genetics, quite a bit, and survey methodology. So some references on generalized score test is there. And because each of the topics are so huge, I won't have time to mention. So spatial econometrics, which plays a very important role, and Luc Anselin, he is quite famous geographer, economic geographer, and he's a National Academy member. So they have fantastically used Rao's score test in spatial econometrics. The econometrics is old subject compared to spatial econometrics. So spatial economics is playing a major role now because now we have spatial data. And survey method quasi-score test. So John Rao, J.N.K. Rao, and they have a fantastic review paper. Both of these papers are really worth reading it. So one of our friend, Anil Bera from ISI, and he had quite a few work, and along with Anselin and Amanullah and so on. So these are some of the references you can see published in some of the top journals, and sufficiently some of them are new, not all. Okay, so now a couple of other things I will mention which are non-technical, like many of you here, including some of the faculty, probably are not familiar that Professor CR Rao, actually we had in our university, University of Connecticut, we have a colloquium program called Pfizer Colloquium. So I'm giving little bit advertisement here for our department, but I think it's very important for you to look at this because ASA has a project that all of these eminent researchers, they give actually lecture at University of Connecticut, and we had 25th so far. The last one was Grace Waba, and before that Efron and all you can think of, D.R. Cox. The CR Rao is the only person who came and gave 2 Pfizer colloquium sponsored by the Pfizer pharmaceutical company. That you can actually, let me see whether, so at this point I am the in charge of this colloquium, and so we'll have 25th. So 24th was Grace Waba. Before that, Pranav Sen, Steve Feinberg, and all the names many of you can recognize. I mean, David Brillinger. So these, whenever it's written link, you can click and you can see this whole interview and about a topic. There are 2 parts. The first part is actually a presentation and second part is interview. Both are very useful and they are available in the link in the YouTube. So I know these days students, everybody use YouTube, I'm sure, and therefore I strongly encourage you to watch some of these and also request the professor to show it in a class. It will be, all of them will be very interesting because we are trying our best to preserve it. Okay, so this part is actually stand alone, and I was motivated by Partha's request that you can go over Dr. Rao's work in Inference, but you can, if you wish, you can do some of your own work. And that I took it as a challenge, kind of, within myself, of course. So one of my students, former student, he is now associate professor in Kansas State University, Go-Young Go, originally from Korea. So we wrote quickly, and it's still incomplete, so it's not a paper yet. So Kramarov lower bound, we already talked about it, and beyond. So beyond is the key word here, that is where it is going. So it's not a dead end. I mean, he did it at the age of 22 in 1942, but the question is, we all teach in class, but we stop at that time, and then we expect solving standard problems. But then there are a lot of work, even in Indian statisticians are done by Anil Bhattacharya, called Bhattacharya bound. There are many directions. But it's interesting, once you think of this whole mean square error idea as a decision theoretic framework, like a loss function, and then you can extend this thing is many ways. You can apply these to other non-Euclidean space, manifold, and so on and so forth. Okay, so now I'll be little formula I'll talk about. First page, first part, no formula. Derived one of the most important inequalities in statistics using the concept of Fisher information, often referred as Kramarov lower bound or CRLB. CRLB provides lower bound on the variance of any unbiased estimator. In other words, CRLB provides the minimum expected loss of unbiased estimator measured by the squared Euclidean distance. Now here, I'll just pause for MSc students, probably don't have any course on decision theory. So in a decision theory, what we do, we think of everything, one of the component, it's really an inference, but component is the loss function. And loss function is extremely used in economics, where they use the phrase utility function. I mean, statisticians are always little pessimistic. We use bad phrases. I mean, computer scientists are very smarter. I mean, they use much better, and you will see some of these. Like we call variable selection, they call feature extraction. But they are the same thing as long as you know the terminology. So same thing, the utility function in economics, they are better than statisticians, and we call loss function. That means we are always prepared for the worst. That's why we call minimax theory. Why minimizing the maximum? That means we are very conservative. But anyway, that's our background. But these days I mix everything, use computer science literature, because too big as a data scientist, that's the only word people like it, because they are more buzzword going on. So in other words, CRLB provides the minimum expected loss of unbiased estimator measured by the squared Euclidean distance. In this talk, we introduce a general information inequality using a large class of loss function called Bregman divergence. So I'll introduce something called Bregman divergence, which is extremely popular now in machine learning literature, in clustering, classification, and so on problem, because it has advantage. You can move away from non-Euclidean geometry, because many of these data we are getting, like data of objects, object-oriented data, shape analysis, shape of a tumor. In this case, standard inference cannot be done. So in fact, CR Rao thought of that much before. That's why he actually developed, soon after the Fisher information, he developed the Fisher-Rao metric, which are extremely popular now in statistical shape analysis. So CR Rao comes again and again. Even if we try to do something new, the source, if you dig, it will come from his idea. So I'll talk about this Bregman divergence. It's not really hard. So even if you have never heard, some of you, probably bear with me and then you'll follow. So let's start with now formulation. X be a random variable with probability measure p theta. Theta belongs to a parameter space, script theta. T is a T of x be an unbiased estimator of g of theta. G of theta is any function. We may be interested in theta, theta square, and a polynomial function, or even linear function. That's expected value of t. T is an unbiased estimator. So we can go through our Blackwellize and then find a nice estimator. But then still, if p theta be the density with respect to upper, so this is the density, this is the probability measure. Suppose expected value of this is 0. Again, this is the score function. So score functions will pop out everywhere in Fisher information and Rao-Fisher metric also. The Kramar-Rao lower bound is then obtained as this. This formulation you have seen in many places. I theta is the Fisher information matrix. You can write this way or minus del 2 of that. And the regularity conditions come very naturally, that you can differentiate within the integral sign and so on and so forth. So it's the Fisher, G prime theta is the score function. So the inequality. So now I will actually develop a new measure. So ultimately, when you have a squared distance, we call Euclidean distance. If it is a L1 distance, it's an absolute value. And therefore, you can have different type of distance depending on what kind of space you are working on. So suppose d of xy is a divergence measure or simply a loss function, I can talk about that, between x and y, such that d of xy is non-negative, where the inequality holds if and only if x equal to y. If your y is unknown parameter theta and x is your estimator, then clearly your estimation is perfect, that means no loss if the divergence between these is 0. But clearly there will be not perfect, so there will be a deviation of that. And equality of course holds when your estimator is same as your parameter. Now we define little modification you have to do, because this dxy will be non-negative, but square root can be negative. So we define a quantity called SSR dxy, which is the sine function x minus y square root of this. It's called the sine square root of dxy. Now all of you should know, in fact the proof of that is based on Cauchy-Schwarz inequality, Rao-Kramer inequality, or part of Jensen's inequality. So Cauchy-Schwarz inequality leads to this quantity where mu of t is expected value of t and mu of s is expected value of s. So here taking s equals this and dxy equal to this, which is called quadratic loss, equation 1 yields Kramer-Rao lower bound. So equation 1 is just a generalization of Kramer-Rao lower bound, but it actually gives you more. I'll tell you next. Okay, so by using Bregman divergence and the something Holder's inequality, we develop a general information inequality.
So which is the Bregman divergence?
Yeah, here is the definition. So definition, suppose we have a function from the parameter space or any to real line. Its range, domain is this parameter space or something where it is applicable. It's a strictly convex function on a convex set, omega subset of Rm, assumed to be non-empty and differentiable. Then the Bregman divergence is defined as Bd psi xy as psi of x minus psi of y. It's really a vector. You can have vector of dimension 1 also. X minus y transpose del. So this is called the gradient vector, because now you have a vector. So x and y, the Bregman divergence under a psi function is really first order Taylor's expansion. You can see that. So del psi represents the gradient vector of psi. The Bregman divergence can be interpreted as the difference between psi x and its first order Taylor's expansion at y. So let's draw a picture, then it will be absolutely clear. So Bregman divergence measures the ordinate distance between psi x and the tangent line of psi at y. So here is a convex function that could be treated as a loss function. Like even the likelihood function, when you take a negative likelihood, it's a loss function. So you can think of different types of loss function depending on the scenario, depending on the problem. So the Bregman divergence of this is plotted here. This particular loss function is called Linux loss function. That means in one direction it's a linear, other direction is exponential. So the use of that is when underestimation and overestimations are paid unequally. So for example, your objective is to estimate the height of a dam, water dam, and then if the height is small, then there will be massive flow of water and that will damage a lot of human lives and so on. So loss is much more. Whereas if it is higher than the sea level or any other water source, then you have the cost of that. So overestimation and underestimations are paid unequally. So that's a scenario where these are used. This loss function was heavily studied by Varian, Hal Varian, who is one of the top data scientists. Okay, so now you can see some example of psi x. So if you take square x square, squared error loss, then if you take a quadratic form, then you get Mahalanobis distance. So Mahalanobis and Rao are always connected in some fashion, and I'm sure Praval will mention some of these ideas, I'm guessing. Then this is a very popular loss function, Kullback-Leibler divergence. Then it's called Itakura-Saito and weighted Linux, and there are some other. Okay. So the signed square root Bregman divergence has this definition. Since this is greater than or equal to 0, this is always well defined for any psi. So Bregman divergence has enjoyed considerable success in the broad field of machine learning, including clustering, classification, and kernel learning. So there is a nice big paper by computer scientist group, Banerjee, there are UT Austin and Minnesota, in Journal of Machine Learning, then Kulis et al., and then these are some of the key references. Then me and my student from his thesis, we had quite a few work, but these two are completely related. That one was published in Journal of Multivariates. So we have developed application of these in model diagnostics and high dimensional regression modeling. So especially in big data problem, when we try to optimize like L1 penalty or L2 or elastic net, these Bregman divergence plays very important role there. So pretty much done actually. So let x be a random variable with these, and t is an estimator such that expected value is mu t theta. S is a random variable such that expected value is mu s. Now in typical Raos Cramer-Rao lower bound, it is called unbiased estimator of 0. But it can be unbiased estimator, need not be 0. It could be biased estimator for mu s, where mu s is a constant that is free of theta. That is the critical assumption. That means we have an estimator unbiased for mu t theta. S is a function of x and the theta, but its expectation is free from theta. Then for Km greater than or equal to 1 and this condition, Bregman divergence yields a general information inequality as follows. So this inequality extends Rao-Cramer inequality and extends many other. The proof is not difficult, but of course I won't do that using Holder's inequality and Jensen's inequality.
Sir, the expectation of S, the mu s,
Yes.
is free from theta.
Yes.
Will this expectation give any information? I'm not talking about future information.
No, it is more general. So that means it did not be unbiased estimate of 0.
What is the meaning of this expression?
Which right side or?
Expectation of all these things.
This expectation is that SSRI defined, and in special case it will be very clear. In the special case when k equal to m equal to 2, and if you choose psi x equal to x square, then the Bregman divergence inequality produces many well-known lower bounds for variance. So this is more general than variance. Say for example, again, if s is 0, then expected value of 0. So mu s is just free from theta. Yes, that is more general. K equal to m equal to, and this, then you get the Cramer-Rao lower bound. Now, other bounds like Chapman Robbins also taught in, when I took the first course from Malay Ghosh, he taught these things. And then if you define these, then this form, that is called Chapman Robbins. So everything is a special case of my general information inequality. And if k, uppercase k is the matrix Kij, and Kij has this formulation, and then C equal to this, then you get the Bhattacharya lower bound, which is done by Anil Bhattacharya. At that time he was in Ramakrishna mission. So S will be in that case, and then again it follows immediately from the Bregman divergence information. So the thing which we have achieved here, extending many inequalities, plus defining a new concept of generalized Fisher information. And I'll tell you more of that. Then 1997, much recent work, compared to Bhattacharya bounds, So if you define this and again this and take this, then this reduces to this form. Now all of these, some of these inequalities are heavily used in electrical engineering literature. So other interesting decision theoretic point of view, that if delta x be an estimate of theta, we define, remember that the loss function is now the Bregman divergence. Because what is the loss function? It's really you have an estimator and you have a parameter, some kind of a distance or divergence between that. The difference between divergence and distance, divergence is weaker because all you need non-negative things. So, which includes square error loss, Kullback-Leibler and so on. Define Bregman divergence risk function. So, what is that? Students may not be familiar. What is the risk function is nothing but the expectation of the loss function. So, when you take the expectation of the loss function, you get a, for the Bregman divergence as a loss, then you get the risk function. So, we have a lemma here that then for any convex function psi, the risk function of delta x theta can be written as delta x mu delta plus Bregman divergence between mu delta and theta. Because of that behavior, just like a square error, it splits into those two parts, because that's a very interesting property of the Bregman divergence. Apply this lemma to Bregman divergence inequality yields a general lower bound for the Bregman divergence risk as follows. So earlier it was more on the variances, mean square error, now the risk function. So this is the lower bound, and we now introduce the Bayesian version of information inequality. So what is the Bayesian version of Kramer-Rao lower bound or any in general information inequality? In that case, to establish that, and of course Bayesian methods we do have now both information from the likelihood function and another layer of information called prior information. So combining these two layers, we have more information. So Tx be an estimate of g theta, not any more unbiased. Pi theta the proper prior density, suppose. E pi be the expectation with respect to the prior pi. E theta expectation with respect to the likelihood function p theta. And then we have this theorem that Km, and then this same condition, the Bayesian Bregman divergence information inequality will be of this form, where S is this and mu S equal to this. So mu S is not 0. Now, in 1995, there is a nice paper by Gil and Levitt in Bernoulli, who introduced the Bayesian CRL, Kramer-Rao lower bound. But our method actually extends all of these naturally, because we are going away from the square error loss to Bregman divergence law. So Bayesian CRLB has, this is the, so if someone asks what will be the Bayesian Kramer-Rao lower bound, the difference is now you define S earlier just del theta log of p theta x, now p theta x times pi theta. Suppose that this will be 0, and that's the regularity condition of even the standard Kramer-Rao, taking k equal to m equal to 2, and then this Bayesian Bregman divergence will be now of this form. So this is the Kramer-Rao lower bound for the Bayesian version, where I theta will be this square and then g prime theta is this. So now we need information extraction both from the prior and the likelihood. So which actually plays major role in coding theory and communication theory, because if you have prior information, then you can pass this more efficient way. So now some of the old results you can obtain, like Hodges and Lemon in second Berkeley Symposium, they proved the admissibility of estimator using the Kramer-Rao lower bound. So now we can actually show the Kramer-Rao lower bound to show the admissibility for quadratic loss. Our result can be used to achieve the admissibility for a general class of loss function that belong to Bregman divergence. Now, Traditionally, this was a very important problem, but unfortunately, these days, admissibility becomes a less important problem. Okay? But still, when you find an admissible rule, it's always performs really good because there does not exist any other estimate which is better than this. So our result can be extended to multi-parameter cases using Bregman matrix divergence. So now all the loss function I talked about on the parameter vector, but we may be interested in many problems. In fact, CR Rao had some of the multivariate problems, especially with Krishnaya. They were doing matrix variate problems. So in that case, your parameter is a matrix. And in big data problem, especially when you are representing the data in a tensor form, then matrix estimation becoming a very, very important issue. So corresponding loss function can be used. And there was a 2009 paper where this group also introduced something, another interesting coming from statistical physics called escort distribution. I don't know whether anybody is familiar with that. With escort distribution, currently we are working on using the Bregman. So therefore, we can apply to many other situations, like another CR Rao with Patil works on weighted distribution. So escort distribution is kind of a weighted distribution. And it comes directly from, okay, so I stopped this thing, just some references. This is Journal of Machine Learning, IEEE Signal Processing. So you can see the variety of the journals. Our papers were more traditional statistics, but now we are working on some of these JMLR paper. So these are so I'll stop at this point. Remember 45, CR Rao's paper was published in the Bulletin of the Calcutta Mathematical Society, that nobody mentioned, but information and the accuracy attainable in the estimation of statistical parameters. So 45 and today is 2000.
Platinum Jubilee.
Yes, Platinum Jubilee, yes. And I can see now another 50 years it will continue. May not be by statistician, but it will be done by more data scientists, electrical engineers. Everything is mixed up in that sense because communication theory, coding theory, everywhere it can be, because the lower bound still plays such an important role because you cannot do anything better than that. Okay, so I'll stop.